You're at a buffet and you grab the tastiest looking foods first. You don't think about balance or nutrition, just what looks best right now. And that's greedy. And hey, maybe you get the perfect plate, or maybe you end up with 5 types of desserts and no protein. A greedy algorithm makes the best possible choice at every step. No looking back and no thinking ahead. It grabs what looks best right now and hopes that it leads to the best overall solution. And sometimes it actually works, sometimes it completely fails. This video is about understanding the difference and when you should be using greedy. Say we have a schedule and we have a bunch of events that we need to attend, and each event has a start time and an end time. Now, we want to go to as many events as possible, but we cannot go to 2 events at once. So basically, if there's 2 events that are overlapping, then we can only go to one of them, right? And the question is, what is the maximum number of events we can go to? To start the problem, let's draw out the times on the timeline so we can visualize what's really happening. Now, the idea behind the greedy solution of this problem is that at each moment we choose the event that has the earliest ending time. Because if we choose the event with the earliest ending time, then what happens is we have more time to go to other events after this event. So since we want the events with the earliest ending time, we'll just sort them by their earliest ending time. This way, when we loop through all the events, then we will get the earliest ending time first. So from here, we can start the greedy algorithm. So we will go step by step and look through each of these events and see which one is suitable to go to. So since we've sorted them from earliest ending times to latest ending times, then when we look at this one, this is the first one we get to, since this one has the earliest ending time, right? And we see that there's no event that overlaps with this one, so we choose this one as our first event that we go to. Right, now we're looking at this event, since this one has the second earliest ending time. And now we see that this event does indeed overlap with the previous event, so we cannot go to this one. And again, once we get here, because this one's the next earliest ending time, we see that this one overlaps a lot with this one, so we cannot go to this one either. Now, when we look at this one, which is the next one, we see that it does not overlap at all with the event that we went to. We don't really care about these 2 events since we didn't actually go to them too, so which means that we can go to this one since it had no overlap with the one we went to. So now we look at this one. It doesn't really matter which one you look at first, as you'll get the same solution since these 2 have the same ending times, but let's just say we look at this one first, and we see that this one does indeed overlap with the previous event we went to, so this one is a no-go. And now looking at the last one, we see that this one has no overlap with the event we went to previously, so we can go to this one. So this means that there are 3 events in total that we can go to. And notice how at each point in time, let's say at this event, when I was looking at this event, I was not worrying about what was going to happen after, right? I was only worried about if this event overlapped any others. So for example, when we got to this one, when we got to this event right here, right, I was not worried about this event right here or this event over here. I was not worried about the future, right? I was only worried about if this event overlapped any other events that we already went to. And since it doesn't, then we can choose this one and move on to the next one. Now, greedy is like a double-edged sword. On one hand, it's extremely useful for certain types of problems, and usually when you can use greedy, the solution's very clean, it's very simple, and it's very elegant. On the other hand, greedy can lead to trap solutions that don't work for the problem, and it's very important that you can tell when greedy can be used. So I'm going to be going over a problem that looks like it can be solved using greedy, but in fact it cannot, and it fails. Now, let's say you have a bunch of coins, right? And each of them fall into one of 3 categories. It's either worth 1 cent, 3 cents, or 4 cents. Now, let's say you want to have a total of exactly 6 cents. Now, I want to ask you, what is the minimum number of coins needed to get to this 6 cents? Our first thought could be a greedy solution, where we take the highest value coin that does not exceed the target value. But as we can see, this doesn't really work because first we would choose 4 cents, since 4 cents is the highest value coin that does not exceed 6 cents. And then we can't choose 3 cents or 4 cents because adding those to 4 would both be greater than 6. So now we have to choose the 1 cent coin. So then that brings our total up to 5 cents, and then we have to choose the 1 cent coin again. So that would bring our total up to 6 cents. So that would be using 3 coins, 1 4 cent and 2 1 cents. The actual optimal solution is to just take 2 3 cent coins, as this will total to 6 cents and it's only 2 coins. Now, an actual solution that works would be dynamic programming, which is beyond the scope of this video, but if you want a video on that, you can just comment and I'll make one. This just showcases the fact that greedy, while being really powerful in solving some problems, can also be really bad if you don't use it correctly and if you don't correctly decide when it is appropriate to use it or not. Now, the best way to learn is through example and through doing problems. So I'm going to be doing a problem and I'm going to be full solving it so that you guys can see what the process looks like for me. Now, a few things that I want to touch up right before we code this problem, and that is that problem solving always comes before the code. If you have a clear solution in your head, then coding it out will be much easier and much quicker. It's important to know that not all greedy problems require mathematical proofs of correctness, and it's often sufficient to just intuitively convince yourself that it's correct. Alright, let's start working on the problem now. So for the example problem, I'm going to do this one, USACO 2022 US Open Bronze Problem 1. I think this is a pretty good problem to show what a greedy solution looks like and how to think like greedy. I'll let you guys read the problem. You guys can pause the video at whatever time you need to read it, or you can just pull it up on your own screen. But yeah. So here we have the original lineup in the sample, and basically a very important thing we notice is that it's telling us that we can only switch even length prefixes, right? And a prefix consists of a range of cows from the first cow, right? Which means that if we were to swap some things, like let's say we swap these first 4, we can do that, but we can't, let's say, pick this right here and choose to swap it since it's not a prefix and it's also not of even length, right? And we're also known that this number n has to be even. So let's first split this up into 2s since we know this must be even. Now, since we want to think greedily, we want to think in a way, how can we at each point select the best choice without having to look back or look forward, right? And since if we swap a certain amount, let's say we swap this or we swap this much, doesn't really matter. But if we swap this, what happens after, so this area over here stays untouched. If we swap this part stays untouched, right? So now if we go backwards, so if we iterate through these backwards, then that means that once we're done processing one of them, then we never have to look back at it since we only swap things that are in front. So this means we look from the back, and we want as many Gurznies, I'm not sure if I'm pronouncing that right, but we want as many of these in the even places. And the even places is just the second place of these pairs, right? Because this is 1, 2, right? Here's 4, and so on, right? So looking backwards, right? We start with this pair right here. Now this pair, if this is a Gurzny already, then we don't need to do any swapping because it's already in the right spot, and we want to make as many of these in the right spot as possible. Since this one's already in the right spot, we don't need to swap, right? And now we look at this pair. So we look at this. The G is in the right spot again, so we don't need to do anything about these two. Now let's look at this one. Here we have an H here, and we want a G, but if we look at this, what happens if we swap this? Yes, we will get a G here, right, from this G, but at the end of the day, we only care about the total amount of G's in the right position. So when we swap this over, these two H's will come here, right? And when these two H's come here, there's no added G's in the even position right here. So there's really no point in doing this, right? And same thing applies if we have two G's, because if we have two G's here, right, we still wouldn't really have any, because we want the minimum number of swaps. So there's really no point of swapping this here, as it just doesn't do anything because the number of G's in even positions stay the same, right? So this one is done, right? We don't need to do any processing on this one. Now we look at this one, we look at the even position, and we see this one does indeed have a G in an even position where we want it. So this one's good as well. Now this one is the first interesting one. So we have an H here, but we have a G here, and we want the G to be in the even position, right? So now let's see what happens if we really do reverse this right here. All right, I'm gonna erase this. If we reverse this, we see that it ends up looking like this. And right now we don't need to worry about these four right here because they correspond to these four right here. And this is just not what we're worrying about right now. So right now, once we swap this one over here, once we reverse this area right here, we see that there indeed does end up being a G in this position and an H in this position, right? And this is what we want because we want more G's in even positions. So we do indeed want to swap this one, right? And then now we add one to the swap counter. So now let's focus on these two right here because these two are the last two, right? And now when we look at this one right here, we see that there is an H in the even position and a G in the odd position. But remember when we swap this, since we've added this to the swap count, right? So then that means it looks like this. And the one that corresponds to this one right here is these two right here. So since we've already added one to the swap counter, aka the swap counter is odd, all right, that means we've already swapped this one once. So these two positions have flip-flopped, right? So that means when we get here, we really don't need to do anything because the G is already in the right position, right? And we're only counting the amount of G's in even positions. We don't actually care what the actual positions look like. As long as we know there's a G in the even position, then we want to move on. So this one's now good. So then when we get to this one now, we know that there has been one swap total, and since it's two G's, right, like we said back here, if there's two of the same breed, it doesn't really matter because no matter how many times we swap it, right, or no matter how many times we swap it, nothing happens since the amount of G's in the even positions stay the same, right? So now we have a pretty good basis for a solution now, right? And the idea is that, so we're gonna go pair by pair, right? So in each pair, if we see a G, G, or an HH, then we do not want to swap. Because swapping doesn't add any more G's in even positions, right? It doesn't add any more G's in even positions. So there's no point in doing it. And since here it says output the minimum number of reversals, we would just be doing one more reversal without adding any G's. So there's no point. So now we have these two cases, right? There's a GH or HG. Now in this case, we have to keep track of a swap counter, right? Basically, we have a swap counter, and the idea is if the swap counter is even, which means that we've swapped 0 times, we've swapped 2 times, we've swapped 4 times, etc. If the swap counter is even, then when we get to this case right here, we do not want to swap. Because look, if this is the original case, right? Then if we swap it once, what happens? It becomes GH. Right? So there becomes a G in the odd position, H in the even position. Right? If we swap it again, it becomes HG. So when we get to this pair right here, if we see that it's been swapped an even amount of times, that means it looks like this. It looks like HG, which means that we do not want to swap it because there's already a G in the even position, right? But if our swap counter is odd, right, that means that if it's odd, it looks like this. So that means we do want to swap it. So if we see that it looks like this, the pair looks like HG, and the amount of swaps so far is odd, then we want to swap again. And if we see the amount of swaps is even, then we don't want to swap, right? So now the same logic applies here. You can try doing it yourself, but the idea is, again, right, if the number of swaps is odd, then it will look like this, right? And if the number of swaps is even, again, it'll look like these two, right? So if the number of swaps is even, then we want to swap again, because we want to put the G in the odd position, or in the even position, right? And if the amount of swaps is odd, then it will look like this. So we don't want to do anything, right? And we'll just keep the G there. Now I want to point out something quite important, and that's that here when I say, like, when we swap the two here, right, what happens is we don't actually swap. So let me write out a sequence, an example sequence real quick, right? So we group this in pairs. So let's say we're swapping all 6 of these. We'll pretend like this is the first cow in the line, and what happens after, we don't really care, since we've already processed this earlier. Once we get to this point, we're not really looking backwards, right? So what happens here is that when we swap it, right, when we reverse it, let's look at what happens to each of these pairs. So this pair right here went over here. This pair right here, right? This pair right here became this one, and this pair right here became this one, right? Because think about it intuitively, what happens when you're reversing this entire thing, when you're reversing the whole thing, you're really just moving this element to the front and this element to the second front, and so on, like that, right? So now when I say that these two elements are switching, right, you can see that they do switch. At first, this one right here is GH, now it becomes HG, right? And an important thing to know is that we don't care about where this pair is, as long as the only thing we care about is whether or not the G is in even position or not, or what cow is in the even position. Now, when it comes to competitive programming, there are many different coding workplaces that you can use. I just use this one called ide.usaco.guide, and it's just online, and you get a good enough place where if you just create a new file like so, you get a nice place to work with your code. You get an input section here, output section, and you can just run the code quite easily. And you'll see here that the output of the numbers is 6, which matches up with the input. And now that we have our solution thought out, we can start coding. All right, let's start coding. So the input, we're gonna just use an integer for n, and then for the big string of all these cows, we're going to use a string, right? And the idea, remember, is that we iterate through this backwards. Right? And we just check each pair, right? So the best way to do this would be with the for loop, obviously. And we could set the index to n minus 2. So if the index is n minus 2, that means we're always going to be getting out of the 2 cows on the last pair, we're always going to be getting the first cow of the last pair, right? And I is greater than or equals 0, and then I minus equals 2, so that way we go pair by pair. So basically what we're doing with this for loop is we're iterating this element, and then this element here, and this element here, this element here, each time skipping by 2, like that. All right, let's start with our conditions now. So remember, if the pair is two of the same, then we don't want to do anything, right? So if SI equals SI plus 1, right, then there's nothing. I'm also going to add a swap counter because we got to keep track of the answer and how many swaps have occurred. So obviously if this happens, we're not going to do anything. And otherwise, right? So if the first letter in the pair is G and the next one is H, then we'll go into this if statement. So that means if the pair is GH, that means we go into this for loop. And then now if the pair is HG, then we go into this for loop. Now remember, if it's GH, remember if it's GH, then we only want to swap when there has been an even number of swaps, right? So if it's GH, that means if swap counter is even, so if 1 divided by 2, lose remainder 0, then we do want to swap. So we can add 1 to the swap counter, and that's all we have to do. So here, right, with HG, remember it's the opposite. So with HG, if the swap counter is odd, right, that means it looks like this, then we want to swap. So then that's it. It's that simple. Usually greedy algorithms are really simple. There's an error here. Don't know why. Oh my god. And then here we can just output the swap counter. And then that should be all the logic needed. The answer is correct. So yeah, from here, just download the file and submit it. I have no idea why it's called Smelly Butter, but it passes all of them, so that's amazing. Alright, so that's greedy. It looks smart, it feels efficient, but it only works when the problem is built for it. If you understand how greedy works and when it traps you, you're already ahead of most beginners. I'll be breaking down other strategies next, like simulation and graphs, other important strategies for USACO Bronze. If you actually got something out of this, consider subscribing. I've got more stuff coming that'll save you time and confusion. Like if it helped, dislike if it wasted your time, and yeah, bye.